Hello all. In this video we'll discuss about the design of a PV system for your home. By means of a case study, we'll take a practical system and we'll design a PV system for this particular practical application, right? So coming to the case study, a residential house has the following electrical appliance uses. The house for which we need to design a solar power system consists of these equipments: a CFL lamp of 9 watts, 2 numbers, and it will be running for 5 hours a day. A fan of 60 watts which will be running 8 hours a day, and number of fans are 1. And a TV, 21-inch TV, we have the wattage of the TV is 150 watts, and number of hours of working per day is 2 hours, and total number of TVs are 1. There is a refrigerator of 150 wattage, and number of hours of working is 8 hours per day, and the number of refrigerators are 1. And there is one computer of 250 watts, and it will be working 3 hours per day. This is the load of the house to which we need to design a solar PV system. It is proposed to meet the requirement by a PV array, a battery, a charge controller, and an inverter. They wanted 4 equipments in their system, that is PV array, battery storage system, then charge controller, then inverter. The whole system is redesigned so that it can meet 2 extra nights requirement even if there is no sunshine during the day. What is that they are saying here? They are saying the number of days of autonomy, 2 days. Even though there is no sunshine for 2 days, the system have to work. That is, the load have to be met by the solar panels, by the solar system. So what is the only thing that we can do? Here the number of days of autonomy means 2 days. Even though there is no sun, the system have to run for 2 more days. That is, we have to design, the battery is the only key thing here. We need to store the energy in a battery for 3 days, not for single day, for 3 days. Generally we will do it for 1 day. System will be designed for 1 day, but because they are specifying they require 2 days of autonomy, we need to increase the battery size by 3 times, right? Extra 2 times. Say for example, initially if it requires, for example, 100 watt hours battery is required, now we need to put 300 watt hours of battery for that extra 2 days also. It is how we have to calculate the system. Then calculate the rating of the inverter if the power factor at the residential premises is 0.9. Because it is a AC power is used in the home, the power factor issue will be there. In the power factor they have mentioned is 0.9. And we need to calculate the number of PV modules and number of batteries required. And so some of the data given is the solar radiation is available for a period of 6 hours daily. Every day in that particular place we are having a sunshine for 6 hours. And the average daily global radiation incidenting on the solar array is 650 watt per meter square. Then coming to the battery. So they have some batteries. Now we need to choose that battery. Right, we need to use these batteries to design the system. We have a batteries available. It is 12 volt and 100 ampere battery is ampere hour battery is available, and the efficiency of the battery is 85% and depth of discharge is 70%. We have a battery with these specifications available, so we need to use this battery. Then inverter. The input voltage of the inverter is 24 volts and the efficiency at full load for the inverter is 93%. We have this inverter available and we have to use this inverter. We have a charge controller efficiency as 95%, and we have the solar panels available, that is 15 volts, 5 amperes and 75 watt peak solar panels. I already told you 15 volts means voltage at peak power point. 5 amperes means current at peak power point. If I multiply 15 5 that 75 is the peak power. This 75 watt peak panel is available for me. It is the things that I have available with, and now I have to start working with the system. Now this is a system. What is that? We have a solar panel connected to a charge controller, and charge controller will feed the energy into the battery, and from the battery energy will be taken by the inverter and convert it into AC and supply it to your home, right? And we have 4 different points there, A, B, C, D. We need to calculate the energy at these 4 points. That we'll do it in the next slides. If I calculate the energy at point A, I got 2820 watt hours per day. At point B, 3032.25 watt hours per day. At point C, 3567.35 watt hours per day. At point D, 3963.7 watt hours per day. This you will get once you do the problem. We'll do that. Though the charge controller efficiency is 95%, inverter efficiency is 93%, battery efficiency is 85%, depth of discharge is 0.7, number of days of autonomy required is 2, and solar radiation is available for a period of 6 hours daily, and the average global radiation incidenting on a solar panel is 650 watt per meter square in that particular area. Now we need to calculate how many solar panels are required, how many batteries are required. You can see how many batteries are required. What is the rating of an inverter? This we need to find out, right? Now let's calculate the first step, that is the load calculation. As it is given in the problem, they have given the load requirement of a load profile of your home. Now we have to calculate the watt hour rating, energy. We have to calculate the energy. So CFLs, there is a 2 9 watt CFLs working for 5 hours a day. So what is the total watt? What is the energy consumed by the CFLs? 9 into 5 into 2. So 9 5s are 45, 45 2s are 90 watt hours. A fan for 60 watts. 60 watts, it will be used for 8 hours. So 6 8s are 480. 480 watt hours per day, and we have only one fan, that is 480 watt hours. And TV 150 watt hours, 150 watts. So it will be working for 2 hours a day. So it will be 300 watt hours. Refrigerator 150 watts for 8 hours a day. So it will be 1200 watt hours. And computer 250 watts is its volt wattage, as well as the number of hours of working per day is 3. So 250 into 3, 750 watt hours. So if I add up all the watt hour requirement of the individual equipments in your home, you will get the total energy consumed by your home, required by your home. That is 2820 watt hours per day. Every day I require 2820 watt hours of energy, that is 2.82 kilowatt hours per day, that is 2.82 units per day the house will consume. So I need to supply this amount of energy to the house from the PV system, this amount of units to the house. And what is the connected load of your home? How to get the connected load? If you add all the power ratings of your equipments in your home, you will get the connected load. You have 9 watts CFLs 2, so 9 into 2 18 plus 60 1 fan, that is 60 into 1, and TV 1 TV 150 into 1, refrigerator 1 refrigerator 150 into 1, computer 1 computer, so it is 250 into 1. So if you add all these things, you will get 628 watts is your connected load of your home, and this connected load of your home require 2820 watt hours per day, that is 2.82 units per day of electricity my home will require, and this amount of electricity have to be supplied by the solar panels. That is our constraint. So now you see at point A is the energy requirement of your home. So the energy requirement of your home is 2820 watt hours per day. So you need to supply 2.82 kilowatt hour per day, that is 2.82 units per day to your home from the solar panel. Now we have to design the system so that at the end we will get 2.82 units per day to your home, right? Then second one is the inverter volt ampere rating. So the inverter rating will be in volt amperes. So the VA rating of inverter will be, you have a power factor, right? So S is equal to P cos phi, you know it. So S is equal to so you have the VA, you require the VA. P is equal to S cos phi, you know it. That is P is equal to VI cos phi. VI is the S, that is the apparent power, that is P is equal to S cos phi. You know the cos phi is power factor. So what is S? S is equal to P by cos phi, that is S is nothing but volt ampere rating of the inverter, P is the connected load of your home, and cos phi is the power factor. What is the connected load of your home? 628 watts from the previous step. 628 watts is our connected load. And what is the power factor as mentioned in the problem? 0.9. So what is the inverter rating you require? 697.77 volt ampere. So you can choose 700 volt ampere rating inverter. This is it. It is about the inverter rating. And then what is the amount of energy stored by the battery? So the output of the battery is nothing but the input to the inverter, right? The energy stored in the battery is nothing but the input to the inverter. So we need to calculate the energy storage capacity of the battery. So what is an efficiency? Output by input. So efficiency of the inverter is nothing but output by input. What is the output of the inverter? The energy requirement of your home. What is the input of the inverter? The energy stored, the energy given to the inverter. That is the energy given to the inverter means the storage capacity of the inverter. The input to the inverter, input DC to the inverter is nothing but the storage capacity of the battery bank. From that we have to calculate the energy at point B. So it is the efficiency of the inverter is nothing but output AC energy of inverter by input DC energy to the inverter. Output AC energy of the inverter to the input DC energy to the inverter, supplied to the inverter. So the efficiency, so output AC energy of inverter means energy consumed by the home. Input DC energy to the inverter means storage capacity of a battery. So input DC to the inverter is equal to energy consumed by the home by efficiency of the inverter. So energy consumed by your home is 2820 watt hours. Right, you can see it in the first slide, 2820 watt hours per day. Right, so what is the efficiency of an inverter? 93%. So we got it around 3032.25 watt hours per day. So every day a battery bank has to store 3032.25 watt hours per day in order to supply 2820 watt hours per day to the home. Because the efficiency of inverter is not 100%, it is only 93%, right? So the battery have to store the 3032.35 watt hours per day in order to supply 2820 watt hours per day to the home, right? Now third part is the sizing of a battery. Now the inverter is over. Now the third one is the battery sizing. So what is the energy required? 3032.25 watt hours. And we need to design a system. We have a battery. What is the battery available for us? From the problem, the battery available for us is 12 volt battery. But what is the input voltage to the inverter? 24 volts. So the system voltage should be 24 volts. We have to connect two batteries in series to get 24 volts, right? So the system voltage will be 24 volts now. Battery voltage is 12 volts, but the system voltage is 24 volts. Right, so input to the inverter is 24 volts. So the system voltage is 24 volts. So energy required is 3032.25 watt hours. Battery energy requirement. And the system voltage is 24 volts. Now the question is how many batteries and of what size of batteries are required. In order to calculate that, we need to go through different battery parameters. First one is a depth of discharge of a battery. Generally, the depth of discharge of any lead acid battery will be in between 60 to 80%. And the second point we need to discuss is here in the problem we have given 70% depth of discharge battery and voltage rating and ampere hour rating of a battery. These two are also given in the problem. We have a 100 ampere hour 12 volts lead acid battery with 70% depth of discharge. Number of days of autonomy are 2 days of autonomy, which is already given in the problem. So what is the depth of discharge of 70% means the battery capacity is 100 ampere hours, but the usable capacity of the battery is only 0.7 into 100, it's 70 ampere hours is only the usable capacity. Even though the battery can store 70 watt hours, but it can supply only, the battery can store 100 watt hours inside it, but it can supply only 70 ampere hours because the battery cannot be fully discharged. If it is fully discharged, then the performance of the battery will be degraded as well as the life of the battery will be decreasing. That is the reason why the depth of discharge is maintained at 70%, right? Now let's calculate that. So energy supplied by one battery. What is the energy supplied by one battery? Battery voltage into ampere hour rating into depth of discharge, right? So battery voltage will be 12 volts, ampere hour rating will be 100 ampere hours, so it will be 1200 watt hours. 1200 watt hours of energy the battery can supply, but the depth of discharge is only 70%. That is of the amount of energy that the battery can store is 1200 watt hours, but Out of this 1200 watt hours, only 70%, that is 840 watt hours only it can discharge. It can discharge only 840 watt hours. That is, the batteries, the energy supplied by a single battery is 840 watt hours. So now what is the battery storage? What is the energy stored by the battery? It is nothing but the input DC to the inverter. Both are same, right? So the energy stored by the battery is 3032.25 watt hours, which we have discussed in the inverter calculation. 3032.25 watt hours. So the total energy stored, the total amount of energy that the battery have to store is 3032.25 watt hours. But from a single battery can store or can supply 840 watt hours. So how many batteries are required? So number of batteries required is nothing but total energy storage of the battery bank divided by energy supplied by a single battery. Now you will get 3032.25 watt hours by 840 watt hours, which will yield you 3.6. So approximately 4 batteries are required to supply this amount of energy, because we have a 12 volts 100 ampere hour as depth of discharge 70% batteries available, and those batteries, how many number I require? I require 4 such batteries. I require 4 such batteries to meet the energy storage of the requirement. So the main thing is the total number of energy required by the house is 2820 watt hours per day. In order to supply 2820 watt hours per day with an inverter efficiency of 93%, I need to have a storage capacity of 3002.25 watt hours per day. I need to store this much amount of energy. So in order to store this much amount of energy with a 12 volt 0.7 depth of discharge and 100 ampere hour battery, I require 4 batteries. You can see I require 4 batteries. I require 4 batteries to store this much amount of energy. I require 4 batteries to store this much amount of energy. So that if I have 4 batteries, then I can store the 3002.25 watt hours of energy. And when I supply, if I can store this much amount of energy, then I can give 2820 watt hours per day to the home. Right? You understand this? Right. Now, the number of batteries required are 4. So the system voltage will be 24 volts. But whatever is, in order to get 24 volts, 2 12 volts batteries are to be connected in series. I require totally 4 batteries, but the voltage rating is 24 volts. I have a 12 volts batteries. How can I get 24 volts from a 12 volt batteries? Connecting 2 batteries in series. So a string of 2 batteries, we will get 24 volts each. And I require 4 batteries, so 2 strings of batteries. That's 2 string of batteries, right? 2 12 volts and 100 ampere batteries. 2 12 volts and 100 ampere batteries are connected in a series to form a string, and 2 strings. We have 4 batteries required, so 2 parallel strings. Now this is an array of battery bank. A battery bank should consist of 4 batteries in such a way that it should have 2 strings, and each string should have 2 batteries each connected in series, right? And these 2 series strings should be connected in parallel. So what is the final output of this battery bank? Even though it is 100 ampere battery bank, it will produce only how much volt, how much usable watt hour, ampere hour? 70 ampere hour, because of depth of discharge is 70%. So current is same because in a string the current is same because they are connected in series. So from single string we will get 70 ampere hours. From the second string also we will get 70 ampere hours. So combinedly we will get 140 ampere hours. And battery voltage is 12 volts plus 12 volts, 24 volts. 24 volts of voltage across each and every string is 24 volts. So total system voltage is 24 volts, and ampere hour coming out from the battery is 140 ampere hour capacity is available with us. It is about the battery bank. It is how you will design a battery bank. Now the number of days of autonomy. So the number of days of autonomy means the number of days a battery bank can be able to supply the energy to the load even when there is no sunshine. That is, on a cloudy day or when there is no energy will be generated by the PV panel. So the number of days of autonomy asked for this problem is 2. The customer asked for 2 days of autonomy. That is, he wanted his PV system to work for 2 more days even though there is no sunshine on a cloudy day or on a summer or on a winter season or in a rainy season. So a battery bank can be able to supply the energy to the load even when there is a no sunshine for 2 days. So 2 days. So generally we will design this for how many days? For 3032.25 watt hours per day. In order to store 2032 watt hours per day, we require 4 batteries like this. So we require a capacity for 2 more days. That is 2 more sets like this have to be connected in parallel. That's it. So totally 4 into 3, 12 batteries are required. You can see it, right? So the initially on the left side you can see battery bank for load supply without autonomy. If there is no requirement of autonomy, then only 4 batteries are required. If 2 days of autonomy is required, then we need to increase the size of the battery bank by 2 times, right? By 3 times. So you will get this complete 2 more 4 batteries for 1 day, 4 batteries for second day, 4 batteries for third day. So you require this much amount of battery bank. So 12 batteries. So as usual, the watt hours coming from each and every pack will be 140 ampere hour at 24 volts. Since the voltage is same because they are connected in parallel, you will get 24 volts. But what about the ampere hour rating? The ampere hours coming from this battery will be how much? 140 from a array of batteries, from one array of batteries. So likewise there are 3 array of batteries. So 140 into 3, which will be 420 ampere hours available at 24 volts. So there is a 24 volts, we have 420 ampere hours available from a battery. This is what about the days of autonomy. Next, the last one is a sizing of a PV modules or arrays. Before doing that, we need to know the required parameters. The parameters for the PV module sizing: voltage, current, and wattage of the module. We already has given with that. That is, it's the 15 volt, 5 ampere, and 75 watt peak panel is given to us. Solar radiation at a given location and at a given time. For every day, you will be having 6 hours of sunshine every day. That's the data for that place. That 6 hours may vary depending upon the place. In some place it will be 8 hours, in some place it will be 10 hours, in some place it will be only 4 hours also. Efficiency of the batteries, it is already given, that is 85%. Temperature of the module, efficiency of the MPPT and charge controller unit is given as 95%. Dust level in the working environment. So whenever the temperature of the module increases, the efficiency will decrease. And whenever the dust falling on the solar cell increases, then the efficiency will decrease. So these 2 parameters also have to be kept in mind. So PV module capacity should be designed to supply only daily energy requirement of load. So how we will design a PV module PV modules? The PV array should be selected in such a way that the solar energy will be, which is falling on the solar panel, will be sufficient to supply for 1 day's requirement. That is, we require at point A. We require at point A. So 1 day capacity only we will take into consideration. So in case when battery bank is designed for certain autonomy, total energy stored in the battery is much more than the daily energy consumed by the load. Because we have taken 2 days of autonomy here, then we need to design a solar panel in such a way that it need to charge that 12 batteries at a time in a single day. The number of panels also will be more in that case. Right. So now let's calculate the thing. Now so far what we have calculated, you can see it here. We have calculated the energy at point A and we have calculated the energy at point B. Now we have to calculate the energy at, now we need to calculate what is the amount of energy that the solar panel have to supply, right? So instead of, so now we went up to B. So B to C, what is that we have? The efficiency of a battery is 85%. The energy stored in a battery is 3032.5 watt hours per day. But what about the energy supplied to the battery? So the efficiency of the battery is equal to energy storage capacity of a battery by energy supplied to the battery from the charge controller, right? So efficiency of a battery is nothing but energy stored in a battery by energy supplied to the battery from a charge controller. If we know what is a battery, so we need to calculate what is the energy supplied to the battery, which is given by energy supplied to the battery is equal to energy stored in a battery by efficiency of a battery. What is the energy stored in a battery? It is the energy available at point B, 3032.25 watt hours. What is the efficiency of a battery? 0.85. Then you will get 3567.35 watt hours of per day. It should be the energy supplied to the battery. You need to supply 3567.35 watt hours to the battery in order that the battery have to store 3032.25 watt hours. Right, if the battery stores 3032.25 watt hours only, then only we can give 2820 watt hours per day to the home. Right, we came up to point C. That is the input to the battery. Now there is a charge controller. Charge controller is not 100% efficient. It is 95% efficient. So 5% will be lost. So 5% more energy, more amount of energy will be supplied by the PV panels to the charge controller. That is, the efficiency of a charge controller is the output of a charge controller or the energy supplied to the battery divided by the input to the charge controller, which is nothing but the energy supplied by the solar panels. Right. So efficiency of a charge controller is nothing but output of a charge controller by input of a charge controller. What is the output of a charge controller? The output of a charge controller is also nothing but the energy supplied to the battery, whereas the input of a charge controller is nothing but the energy supplied from the solar cells, that is the solar panels. So what we will get now? So efficiency of a charge controller is nothing but energy supplied to the battery to the energy supplied by the PV panels. Right. So we require the energy supplied by the PV panels. So what should be the energy supplied by the PV panels? Energy supplied to the battery by charge controller. Efficiency of a charge controller. Energy supplied to the battery is 3567.35 watt hours, whereas the charge controller efficiency is 90%. So you will get 3963.7 watt hours per day. Now you understand clearly here. In order to supply 2820 watt hours per day to the house, the solar panels has to generate 3963.7 watt hours per day. Right. In order to supply this amount of energy, solar panel have to generate 3963.7 watt hours per day. So in other words, in order to give 2820 watt hours per day to the home per day, the battery with 2 days of autonomy, the battery bank have to store 3032.25 watt hours per day. In order the battery bank have to store 3032.25 watt hours per day, because the efficiency of the battery is not 100%, it is only 85%, there will be 15% losses. 15% more amount of energy have to be supplied by it. So 15% more energy will be 3567.35 watt hours per day. So charge controller have to supply 3567.35 watt hours per day. Even though charge controller is not 100% efficient, it is only 95% efficient, so there will be 5% energy loss. So 5% more amount of energy have to be supplied by the solar panels, that is 3963.7 watt hours per day have to be supplied by the solar panels in order to give 2820 watt hours per day to your home. Now let's calculate the number of solar PV panels required. So for that we first calculate the ampere hour required by the PV panel. AH that have to be supplied by the PV panels. So AH means ampere hour rating. How will you calculate the ampere hour required by the solar panel? Ampere hour that has to be generated by the solar panel means total energy supplied by the solar panels by system voltage is 24 volts. So watt hour by voltage will give you ampere hour. So 3093.7 watt hours by 24 will give me 165.1 ampere hours. So other factors that degrade the solar cell performance is high module operating temperature, dust settlement on PV module, which the 2 points which we already discussed, and we are not taking these two things into consideration, because once we take these two things into consideration, then the ampere hours that has to be supplied by the solar panel will be further increased. So we need to produce more, we need to use more and more number of panels, right? So these parameters would increase the amount of ampere ratings produced by the PV module. Practically speaking, they will be there, but for the time being I am not considering these parameters. So because in a residential apartment the dust is not a big problem, whereas the module temperatures, because we are keeping it on an open air, the air will cool down the module. So I am neglecting these two parameters. So in this example, the PV module performance degradation parameters are considered 0. So the ampere hours required by the PV panels is 165.1 ampere hours. So assuming, so we have 6 hours of sunshine per day. 6 hours we are getting the solar energy. So we can generate the energy for 6 hours. So total amperes needed. We need to calculate total current that will be generated by the solar panel. So total ampere hours by total hours of sunshine. So total ampere hours are 165.1 ampere hours by 6 hours. 6 hours the sunshine will be 6 hours the sun will be shining. For 6 hours the solar panel is supplying the energy. So by 6. Then you will get per hour. Per hour you need to supply 27.5 amperes. So you require 27.5 amperes is needed from the solar panels. So solar panel have to produce 27.5 amperes per day. So what is the solar panel available with us? We have 75 watt peak solar panel available, which consists of 15 volts and 5 ampere ratings. So each solar panel will give me 5 amperes of current. But how many amperes I require? 37.5 amperes of current required. So how to calculate the number of panels required? 27.5 by 5. I will get 5.5, approximately 6 panels are required. I require 6 panels. I require 6 panels to produce 27.5 amperes of current. But what about the system voltage? 24 volts. But what is the panel available with me? 15 volts. So to get at least 24 volts, how many panels I require badly? 2 panels. So 6 into 2, 12 panels are required by me. Right, 6 panels to supply the current rating and 2 panels to supply the voltage rating each, and 6 panels to supply the voltage rating. That's why I will get 12 panels. So I require a string which consists of 2 cells, 2 PV cells, 2 PV arrays, and likewise I require 6 different strings. The number of strings in this PV array is 6 and the number of PV modules in each string is 2. So you can see likewise I have given the arrangement. What is that? I have taken one single string, that is 15 volt and 15 volt, it is 30 volt, and the current rating is, from each panel I will get 5 amperes. So from a single string I will get 30 volts maximum voltage and 5 amperes is the current, maximum current I will get. Right, you understand that, right? From a single module I will get 15 volts and 5 amperes. That is the panel I have available with. Right, if I connected these two in series, then voltage will be multiplied by 2 and current will remain the same. So from a string I will get 30 volts and 5 amperes because the current is constant in series. That's why I will get 5 amperes and voltage will be added and I will get 15 plus 15, 30 volts. I require only 24 volts, but I have a panels which can give me 30 volts voltage. It's fine. And then there will be 6 strings to satisfy the voltage requirement is satisfied. Now what about the current requirement? I require 27.5 amperes. That is, I require 6 panels. 6 strings I require. 5 into 6 will be 30 amperes. So I require at least 30 amperes current. So I require 6 strings. That is, each string will give me 5 amperes and 5 strings will give me 5 amperes each, and that's why 5 into 6 will be 30 amperes. So finally my solar panel is designed in such a way that I have 30 volts voltage output and 30 amperes current output from the solar panel per day. It is how it will be designed. Clear? That is totally how many ampere hours that my solar panel is giving now. Amperes are 30, number of working sunshine hours are 6. So 30 into 6 will be 180 ampere hours is given by my panel. What is the actual required by the panel? 165.1 ampere hours, but I am supplying 180 ampere hours, which will be more than enough. Right? It is all about the solar system design. Now complete structure. So as I told you, we have a solar PV array which consists of 6 strings and each string consists of 2 modules in series. Right. So the power rating of each and every module will be 15 volts and 5 amperes, and thereby the total power, the maximum power from a single module is 75 watt peak. So there are how many panels are there? 12 panels. So you will get the required power from the solar panel. And the next one is a charge controller. The charge controller, what is the voltage required by the charge controller? 24 volts. The system voltage is 24 volts. What is the ampere that is generated by the solar panel? 30 amperes. So voltage is 24 volts and the ampere rating is 30 amperes. And coming to the battery bank. The battery bank is each and every battery. I have a 12 volts 100 ampere hour battery. So number of batteries connected in series are 2 to get 24 volts. So 6 such strings I require. So 12 batteries I require. Similarly 12 panels I require. Right. And coming to the inverter. Inverter, I have a 700 volt ampere inverter rating. The system voltage is 24, input of the inverter is 24 volts DC, whereas the output of the inverter is 220 volts AC. And with that it is supplying two CFL lamps of 9 watts capacity, 160 watt fan, 150 watt refrigerator, 150 watt TV and 250 watt computer. It is how the complete structure will look like. So in between we need to keep some protective devices. In between the solar panel and the charge controller we have to keep a fuse and a switch to disconnect and connect the charge controller from the PV array. And we need to go for a surge protector to prevent the solar panels from the lightning strokes. We need to use a surge protector here. And then there is a switch between the charge controller and a battery. Depending upon the requirement we need to switch on the on off the switch. And we have an inverter and we have the complete load. It is how the complete structure of a solar system will look like. So in this way you have to design a solar system for your home. Not only for your home, for any application you need to design in this way. Right. With this we have completed the design of a solar PV system as well as the 5th unit of the solar energy conversion. With this the syllabus is completed. Thank you.